We hear you.
Yes, well, uh, I think we can continue with the lecture. So now I will talk about NAMD, which is another common package for molecular dynamics, and is also very well optimized. So NAMD includes several versions, and the way to run that depends on the version that you want to use. There is a single node version, a multi-node GPU, and also an NAMD can run on KNLs. So in these two articles, the ACC and this one from the journal, International Journal of Supercomputing, you can find some details on how NAMD was implemented, on how the forces and the energies can be computed. So NAMD is a message-driven communication implementation. So, and how it works. So this is different from the MPI version that we saw in Amber, because in MPI, one sends the messages around, and then some process is expected to receive that message. And on the while, if the message is not received, then it creates an idle time. So message-driven scheduling tries to avoid this idle time because it creates a bunch of tasks, and then the processors are expected to fetch a task once they are free, and that it's the main advantage of NAMD, and this was very interested at when NAMD was recently launched. So you can find the details of this type of protocols in the cited literature here. So this is one way to run a NAMD using multiple nodes, and this implementation can also run, of course, on a single node. So here for multiple nodes, I'm specifying here the number of processes. In this case is 56, because there are 2 times 28 cores on the Kebnekaise standard nodes. And this is the most recent version that is installed on the focal setup. So in the case of GPUs, the things change a little bit. So besides specifying the number of processes, in this case 28, so we specify the number of GPUs that we want to use. In this case, I'm specifying the K80 nodes or GPUs, and also the tool chain that is required for the CUDA NAMD. Notice here that the CUDA part is included. And notice here that the NAMD version is the no MPI version. So you can run NAMD with the default case by using NAMD plus 28, your configuration file, and this is some output file that I'm printed out. And with the default version, you will get some performance, but if you add this line here, you will get about 10% or even more speed up. So these lines here are recommended. The set CPU, affinity, and idle pole, and device, the CUDA visible devices. So a comment for NAMD is that it doesn't run entirely on the GPUs, as in the case of Amber that I mentioned before. Yeah, so NAMD will run some part on the GPUs, especially the short range interactions that I mentioned when I showed the loop. And the rest of the interactions will be run on the CPU side. So that's why I'm specifying here the full 28, because NAMD will use the CPU as well, not only the GPUs. There is a question on the chat. It says, shouldn't be SRAM NAMD for the GPU part, not, because this is the single node, right? But for these multiple nodes, yes, because in this case, SRAM will take this number here for the processes. And in the case of the single node, not, because this is a shared memory implementation, which is expected to run only on a single node. That's why SRAM is required here. And here I'm specifying the number of processes. So NAMD will scale if the number of patches is larger than the number of processes, and you can see this information at the beginning of the log file from NAMD, and you can check what is the number of patches that you get for the run, and you can tune that in NAMD. For instance, you can dedicate some number of processors to solve the PME long range part by using these lines here. And the CUDA version also offers the feature to offload some PME to the GPUs. So for instance here, use CUDA PME on and PME offload low on. So, but notice here that for using this offloading, one is expected to use only one MPI process, and it depends on your system, because if your system is very large, you will benefit from using several MPIs, not only one. But if your system is relatively is small, then using a single GPU and then offloading the PME part to the GPU as well, then you can get some speed up. So very useful is that the call bars restraints can be run on the GPUs. So there is no problem. You have several call bar restraints, and because they are parallelized also for the GPUs. So this is one thing from the codes that I will present today, is that some of them offer the feature of offloading different parts of the codes manually. So for instance, in the present case, NAMD can offload the PME to the GPUs. It can also offload the bounded interactions, yeah, but they have some constraints in doing that. So in that sense, from my point of view only, is that Amber has been very well optimized because the user doesn't need to offload the interactions manually. Amber does it by itself, and the efficiency or the performance that you have seen before, it's quite good. So more information about the performance of NAMD, how to tune that, it can be found in these 2 pages. So this is one possibility for using the call bars. They can run on GPUs. The call bars can be more complicated than this. And in this case, I present you a restraint for a channel which is asymmetric. So more information on call bars can be found in this page here. So, and this is some benchmark for NAMD using different implementations and also running on different architectures. This is the shared memory protocol that I show you that doesn't need the SRAM. And you can see here the performance. And this is the MPI version where I use the SRAM, right? And I'm running the Broadwell implementation, and this one is especially interesting, is the so-called multiple time step simulations. And it means that upon integrating the Newton's equation, you can set a different time step for including the interactions. In particular, the bonded interactions and the dihedrals and the interactions whose force changes a lot in a very short time need to be integrated more frequently than the ones whose interactions doesn't change considerably in a longer time scale. That's why for the high frequency interactions, you set a short time scale, while for the longer interactions, you set a longer time scale simulations. And especially this is good because the Coulomb force is an interaction that doesn't change too much in short time steps. And here, for the column interactions, you can set a longer time step than for the bonded interactions, for instance. And this allows you to get this type of speed up. So very interestingly is that the multiple time step methodology conserves the energy very well, because this is a symplectic algorithm, and there shouldn't be any problem with energy conservation. So here I'm including also a nice landing code that I myself obtained from GitHub. This is not installed on Kebnekaise. I obtained from the GitHub version at that time. And you can see that on the nice landing, the performance of NAMD was very similar to the MPI and the shared memory version, using only one node, right? So, and you could get some benefit from the nice landing as well in the case of NAMD. So keep in mind the multiple time step. And here, as you remember, I set the CPU affinity in the shared memory version. And if you set that, you will get a 10% speed up about that for the CUDA implementation. So this is NAMD on GPUs, and here I benchmark the Broadwell nodes and the Skylake nodes. You can see that the performance upon using 28 processes and 2 GPUs on each node. And again, here MTS refers to the multiple time step algorithm, and you can also get a further speed up upon using GPUs. This is up to now the best performance that I obtained from NAMD using GPUs. So as you remember, in the case of Amber, the best speed up on the Skylake was about 47 nanoseconds per day. And in the case of NAMD, it was about 20 nanoseconds per day. And the input scripts and the system are very similar to each other. So further resources for NAMD can be found in the NAMD tutorials on this website. From my personal opinion, they are very well written, and you can get a simulation running for the different methodologies very easily for the standard methods. So now let me go to the next software, which is GROMACS. And in this case, GROMACS can run also on several architectures and using different versions. And in the present case, I'm showing you the script for running GROMACS on GPUs. And here I request for 2 GPU cards, and this is the number of MPIs, which is equal to 4, and this minus C is used for the number of OpenMP threads if you want to combine the simulation. This was an old version of GROMACS that was installed on Kebnekaise, but The 2016 is very robust from my point of view. And I don't know if I haven't checked up to now if this is installed on Kebnekaise or if some people have requested for it. So if you need it, you can send a ticket. So, and this is the way to run GROMACS, and you can set several things here. You can set, for instance, the number of OpenMP threads by using the -NT OpenMP, and the number of PMEs that you want to use. And this flag refers to the load balancing setup for making the workload more balanced. So in the case of GROMACS, you can set many flags, and this can make your simulation more efficient. But in general, I would say that if you run your simulation with the default flags, for instance, GMX, MPI, MD-run, and without the NPME and the -DLBS, then you will get a good performance because GROMACS is very robust. So, but if you need more speed up, and you think that you will spend a lot of time with the same system, with the same simulation, then it's a good idea to learn about the different options that can make your script running faster. So GROMACS has some tools to make your application more efficient, to tune the flags for the most expensive calculations, for instance, PME. So here the EMX Tune PME tool, they can tell you the number of PMEs that make your simulation faster. Here, for instance, in the line for the summary of PME, you can see the number of PMEs. In this case, could be 0 or -1. You get a different performance. And then once you get the best number here, you only go and set this number to the -NPME. So this could help you in your simulation. So these are some results for the benchmarking of GROMACS using the version 2016.3 and with a threaded version and the MPI version. So a threaded version is supposed to run faster on the one node only, and this is only a thread here because this version threaded should run faster on a single node than the MPI version. So here in the setup, I'm using 4 MPIs and 7 OpenMP threads. And the performance comparison is between the Sky Lake in orange and the Broadwell nodes in blue. So here I present you a benchmark of GROMACS using the MPI version on a Broadwell node and on a KNL node. And you can see that the performances are very similar. Yeah. And here for the KNLs, you don't need to wait a lot for the simulation to get started. And here I'm also comparing different versions of GROMACS going from the 2016 to the 2019. So In the case of the KNLs, notice that there are some things that change. For instance, here you need to specify the name of the queue, which is KNL, and also the constraints regarding the memory and the type of cluster that you want to use. The present case, I'm using the cache and the quad type. This is the version that was installed on the KNLs. And this is how you can run your script on a single node. And notice here that we are pinning the threads such that they are using 2 threads per core. Now this is the best or the most efficient way to run that on the KNLs. So in order to use the KNLs, you can log into the KNL node on Kebnekaise, and here you can check what modules are available by typing ML spider as usual. And once you get these modules, you can write them in your batch script. Then you can submit your script either from the login node from the KNLs or from the standard login node. And notice, I would encourage you to use GROMACS for this, because the queue for the KNLs is most of the time available compared, for instance, to the GPU one. So it depends on the workflow that you want to follow. Maybe you need a very fast result because you are in the process of replying to a reviewer comments for publishing an article. Maybe you need that the GPUs, but if your simulation can wait a little bit, then using the KNLs would be a good alternative. So this is the performance of the KNLs for a 2 million atoms model, and I obtained this TPR file from a Group Mueller web page here at the bottom, and you can see how it performs using different architectures, including the Broadwell, Skylake, and the Nice Landing. So another benchmark, but this time using a larger number of nodes, up to 3. And notice here that this system is very big, and the KNLs are showing that they could scale up to many nodes. So toolchain effect, if you use some toolchain, the simulation could run faster. Here I'm comparing the version 2019 of GROMACS using 2 tool chains with the same input scripts. So there is a question: does the 2ML atom system need PME? Well, I remember that in this case I ran the PME tool, and it shows this number here. And also I tried different combinations of the PME, and the ones that I presented were the most efficient ones. And this is a good question, because depending on your system, the combinations on PME and also OpenMPs and MPIs could make your simulation more efficient or less efficient. So my opinion is that the combination of these parameters, it strongly depends on the system that you have. No, I don't have any benchmark regarding the plummet. So in the case of GROMACS here, there is a one way to run GROMACS on GPUs by using the default flags. So what it means is that we use srun, EMX MPI, MDRun, and here I'm only setting the number of OpenMP threads and some additional flag for the load balancing. So here you will see how GROMACS will run. It tells you the number of MPIs and the number of OpenMP processes. And also notice here that it tells you that the particle-particle interactions will be run on the GPUs, right? So what happens if we instead use 4 MPIs and 7 OpenMP threads? Then GROMACS will tell you that the 4 tasks will be run on the 4 GPUs, and the distribution will be as follows. So one thing is that when you specify in GROMACS, let me go here. When you specify here for the K80s 2, it means that GROMACS will detect the 4 GPU engines, because here this is the number of GPU cards, and each card on the K80s contain 2 GPU engines, and GROMACS detects these 4 engines, and that's why here GROMACS will use the 4 engines, the full cards, I would say. So this is also the single node, and this will use the 4 engines that I showed you before. So this is the performance for the single node, and I also did a benchmarking for the different GROMACS versions, and you see that the performance changes a little bit. So within the statistical error, but also I found that some of them are faster than the others, especially the latest one that is installed, the 2021. So notice here the performance on the Skylake is much more faster than the others. So in the case of the single node, I also did a comparison between the Broadwell and the Skylake, and also for the MPI and the threaded MPI. These are 2 different implementations, MPI and threaded MPI. The threaded MPI is a layer from OpenMP, from MPI, sorry, that it's supposed to run faster on a single node. And notice here the performance with the threaded MPI on the Skylake with respect to the MPI on the Skylake as well. And for the GROMACS version 2021, which is the latest one. So GROMACS also offers different ways to offload the task on the GPUs. And here I'm showing you the one that we saw before, and this is the default. I will call it the default one because I only need to specify the number of threads. There is a question on the chat. Let me go to it. Okay, there is no question. And this, I will call it the default way to run GROMACS, and it will use up to 4 GPU engines. But you can also tune the type of task that should be uploaded to the GPUs. And if you have some type of architecture where, for instance, the number of GPUs is small, or they are not so fast, and you have faster CPUs and plenty of them, then you can set this GPU task flag, and this will allow you to set the task to the GPU devices that GROMACS detects. For instance, here, the number of MPIs sets the number of tasks. And here I'm telling GROMACS to use the GPU devices 0 to 3, in total 4, to use all these tasks. This is a more specific flag, and fortunately, for the setup on Kebnekaise, this is the default one, so you don't need to specify it. But this is good to note if you go, for instance, to another system and you need to tell GROMACS on what devices you need to run. So what is important here is to set the task that will be offloaded. In the present case, I'm offloading the GPU, the non-bounded interactions to the GPUs, and also the PME part to the GPUs. Then I must set the NPME to 1 because this is the current implementation of GROMACS, and you must set it to 1. And here, when you take a look at the output of GROMACS, you will see that the first 3 tasks, which refer to the PPP interactions, will run on the first 3 GPU engines, while the last one will be reserved to the PME task, right? So in this way, you will run the non-bounded interactions and PME on the GPUs. So the trend in GROMACS was to gradually offload the tasks to the GPUs, in contrast to NAMD, where they try to offload everything from the beginning to the GPUs. That's why in NAMD you don't need to specify what task you need to offload. It will do automatically for you. In the case of GROMACS, I guess they try to do that in a gradual way to support all the methodologies that they have available, and then they are gradually moving everything to the GPUs. So this is the performance comparison. No offload refers to the case where I'm not offloading any tasks to the GPUs, and this is what I show you. And here's where I offload the PMEs as well, and the non-bounded interactions. So you can see the difference in performance, and especially for the Skylake nodes, the performance is quite good, but also notice that the Skylake nodes are not that many on kernel cases, so the waiting time could be longer than for the Broadwell nodes. So in the case of multi-node offloading, you can run the command srun, and also using the different number of nodes and setting the number of MPIs. So GROMACS will detect the GPUs on each node. So there is a guide from the GROMACS developers, and for the current implementation, it's a good idea to read this part, because this includes several tips to make your simulation faster. And yeah. So this is the multi-node comparison for GROMACS for the Broadwell, and using offloads and no offloads. The present case, the system seems to be not that big, so that the scaling behavior is just about 3 nanoseconds per day. So one common mistake from the GROMACS community is when they try to use Plummet and the threaded version in GROMACS. As I said before, the GROMACS has the threaded version, threaded MPI and MPI versions, and Plummet threaded MPI is not supported. So instead of using the threaded MPI, you must use the MPI run, the GROMACS MPI. So some additional information about GROMACS. So recently, for the 2021 version, there are some other features that you can offload to the GPUs, including, for instance, the bounded interactions, the updates for the position and the forces can now run on the GPUs, and also some part of the PME can be run either on the CPU or on the GPU. For instance, here the PME FFT can run explicitly on the CPU, because this part requires communication, and it's a kind of a bottleneck upon running on the GPUs. So you can set that. So it's good from my side that, well, I tried these combinations for Kebnekaise, and fortunately for us, we don't gain a lot if we use these flags, but for other systems that could be the case. For instance, there are several other architectures around the world where you could be running your GROMACS script that would need or would benefit from using these flags. For instance, imagine some architectures where you only have GPUs and a few cores which are not that fast. Then you could benefit from that. Or in another way, imagine an architecture where you have a lot of powerful CPUs, but only one GPU per node. Then, of course, you will benefit from using this type of flags. So additional resources, as I said, there is a guide for running performance simulations from the GROMACS community. And also there is a very well written information from ENCCS, where they show how to run performance simulations with GROMACS. Also, for instance, there are some well-written tutorials for GROMACS when you want to get started. And this is especially good BioExcel website, which includes, in addition to the tutorial, several videos related to the most recent features of GROMACS that are very useful to watch, I would say. Is there any question on GROMACS? Okay, now let me go to the last software, which is LAMPS. And LAMPS can run on different versions, including the MPI, OpenMP, and also recently the Cocos implementation. So this is the module that is available now for LAMPS on Kebnekaise. And here I'm running the MPI version with srun, and I need to specify the number of processes. So in the case of the OpenMP, you will specify, besides the number of MPIs, the number of OpenMP threads, in this case 2. And also I need to set the number of threads with this environment variable equal to 2. And for some systems, if they are not that big, that could be helpful. But for the present system, this showed a 3x slower time than the pure MPI version. So I would recommend the pure MPI or using Cocos, for instance. So some resources for LAMPS can be found here on these tutorials from the Sandia laboratories. And this is a comparison of performance with LAMPS and OpenMM and Charm DOM deck implementation using GPUs. You can see that LAMPS is about 1 nanosecond per day for the same script that we have been benchmarking up to now. And OpenMM is about 2 nanoseconds per day, and Charm DOM deck is 3. So I included in the benchmark folder the script for OpenMM and also LAMPS, but I didn't include the Charm DOM deck. So do you have any questions up to this point? So, okay, let me continue. So, imagine that you are writing frequently in your simulation. So, a good idea in this case would be to use the Scratch directory, which could give you about 10% speed up. And in this case, you put the files on the Scratch directory, you synchronize the parent directory or your current directory to the Scratch one, and then you run the simulation on the Scratch directory. So notice here that I'm using the full node, which will use the full Scratch. Otherwise, the Scratch is used on a core basis way. So you will get part of the whole Scratch if you use less than the full node. And finally, you synchronize the Scratch directory to your current directory. So this is the Scratch memory that you could get. Okay, that's it from my side. I had some information regarding the plugins and tools, and notice that some of them are not installed on our system. I installed them myself. So I will not go on this part, and instead I will start the exercise time, and you can run the scripts that I provided you, and they are in the GitHub repository that I mentioned before. You can clone it, and the part that we'll be using today is this benchmarking. You can choose the software that you want among Amber, GROMACS, LAMPS, and so on. And or in the case that you have your own script that you want to try, then we can take a look at it. So basically, today we will be benchmarking the software. And tomorrow, if you are interested, I will show you how to set up a simulation with NumD, and later on, how to do a QMN simulation with NumD and Gaussian.